So, this lecture is the first lecture in Module 3. We're going to talk about data types, variables, and constants. So, as I showed you before, here's a list of the learning objectives for this particular module. This module has a number of lectures, so it's going to take us a little while to get to meeting all these objectives. But these are the objectives we're trying to meet for this module. It's important to remember that everything in a computer is represented as binary. It's just ones and zeros. And so we need to think about how this actually works in practice to get a good understanding of how data types work. So the question is, why do we care? And we care because ones and zeros are used to represent anything. We can represent pictures, we can represent music. This is why computers can store all this incredible information, is because everything can be encoded as ones and zeros. But the question is, say we want to store something, and this is what's really going to matter for this particular module, is if we want to store something, how many bits do we actually need to represent something? And that question is sort of deeper than it seems at first blush, because the question really comes to, well, how accurate does the representation need to be? Can I actually store this beautiful picture of a mountain using only 8 bits for each pixel? Or do I need more bits than that to store all the colors that the eye can see, and so on? So we need an understanding of how many bits we need to represent stuff, so that we can really understand how the different data types and the different accuracies that they have sort of matter. So, of course, a story. On Christmas morning, my family was trying to decide who would get the first present. And there were 4 of us there at the time. One of my sons wasn't there yet. So we wanted to figure out who gets the first present, and we wanted to do it by flipping a coin. So my son and I, remember, my son, the computer scientist, and I came up with one answer, and the non-programmers in the room came up with a different answer. So you should now pause for a minute and go do the in-lecture quiz to try to figure out how you would use coin flips to figure out who out of 4 gets to open the first present. There are a number of reasonable solutions to this problem. One of those solutions is to treat this like a tournament, your standard basketball tournament, or pick your sport, but it's the playoffs. And so you can do this with 3 flips. You do one flip to pick between A and B. You do another flip to pick between C and D. And you do a third flip to figure out who of the winners of that first round actually finally win and get to open the first present. So this is a really intuitive way to think about it, and obviously people use this approach all the time. But it turns out that we can, I want to do this very dramatically, we can use the power of binary. We can actually do this in 2 flips. But we do it by thinking about how we encode things using zeros and ones. And as you can see from the image on the left, we can represent 4 different things using 2 bits, just by using the combination of the 0 and 1. So we can actually do this with 2 flips by, just set 0 to tails and 1 to heads, flip the coin twice, and whatever encoding you get from those 2 flips, that determines the person. So let's step back for a second and think about, well, if I have 1 bit, how many different things can I represent? And the answer is 2 different things. A 0 means one thing, a 1 means another thing. If I have 2 bits, as we've seen here, I can represent 4 different things. And so there's got to be a general mathematical equation that we can use to say, if I have this many bits, how many things can I represent? And of course there is, and we're going to actually look at a biggest font slide of the entire course. Probably, we'll see. And it's n equal 2 to the b. So what that means is we need b bits to represent n different things. And that's important because the more bits we have, the either larger numbers we can represent, or we can represent numbers with greater accuracy. And that will matter as we decide to figure out which data types we want to use in our programs. So this is a pretty short lecture. Let me recap. N is equal to 2 to the b. So given b bits, we can represent n different things. Now, you might know n, right? You might say, I have 65,535 things to represent. How many bits do I need? That's just the opposite equation. So it's b is equal to log base 2 of n. That's how we do these calculations. So that gives us an understanding of the relationship between how many bits we have and how many things we can represent with those bits. Next time, we will move on and actually start talking about data types and why the number of bits actually matters to us when we consider data types.